Hello everyone. Welcome back to my YouTube channel, Chemical Adda. In today's video, we will understand a very important topic in heat transfer operation, boiling. By the end of this video, you will clearly understand what is boiling and how it occurs, types of boiling, the role of pool boiling, subcooled boiling, and saturated boiling, heat transfer characteristics during boiling, and the effect of surface tension on bubble formation and detachment. Alright, let's get started. First, let's understand what is boiling and why it is important in chemical engineering. So, boiling is a convection process with phase change occurring when a surface temperature exceeds the saturation temperature of the liquid. So basically, boiling is a convection process that involves a change in phase from liquid to vapor. It may occur when a liquid is exposed to a solid surface, maintained at a temperature higher than the saturation temperature of the liquid. And hence, in boiling, heat transfer occurs through a combination of conduction, convection, and phase change. Let's understand this with the help of diagram. So first, heat is conducted from the hot surface into the liquid layer in contact with it. Due to this, liquid temperature increases to its saturation temperature, causing vapor bubbles to form at the surface. Then, as these bubbles grow and rise upward, they stir the surrounding liquid and create convection currents that carry heat away from the heating surface. And at the same time, the change of liquid into vapor requires latent heat, which is also supplied by the heated surface. Thus, in boiling, heat transfer is the result of conduction from the surface, convection due to bubble movement, and the absorption of latent heat during vaporization, and it occurs when liquid contacts a surface hotter than its saturation temperature. Hence we can say that, during boiling heat flux depends on the excess temperature, that is, Tw minus Ts. Where Tw is surface temperature and Ts is liquid saturation temperature. Therefore, in boiling, rate of heat transfer can be calculated as Q is equal to H into Tw minus Ts. Then we know that boiling is the reverse of condensation. And it plays a vital role in many chemical engineering processes such as distillation, evaporation, and steam generation. Now let's understand what is pool boiling. So, pool boiling is the type of boiling in which the heating surface is surrounded by or submerged in a relatively large body of liquid, which is agitated by the motion of the bubbles and by natural convection currents. So basically, pool boiling happens when a hot surface is placed inside a large container of liquid. As soon as the liquid touches the hot surface, bubbles form and rise upward. These bubbles, along with the natural upward movement of hot liquid and downward movement of cold liquid, keep the liquid mixed, and this combined movement of liquid helps in transferring heat efficiently. In short, pool boiling is boiling in a large body of liquid, where both bubbles and natural convection cause the liquid to move. Therefore, we can say that, in pool boiling, liquid agitation is provided by the motion of vapor bubbles and natural convection currents inside the liquid. Then next point about pool boiling is common in chemical industries such as in reboilers and evaporators. Then now let's see what are the different types of boiling. There are three types of boiling. First one is subcooled boiling, which is also known as local boiling. Then second one is saturated bulk boiling. And third one is saturated pool boiling. Now let's understand this one by one. So, first let's understand what is subcooled or local boiling. So, if the bulk liquid temperature is less than the saturation temperature, the process is called as subcooled or local boiling. So basically, when the bulk liquid temperature is lower than the saturation temperature or boiling point, the process is called subcooled or local boiling. In this case, vapor bubbles may form near the heating surface due to the high local temperature, but since the surrounding liquid is still below its boiling point, these bubbles cannot survive. And therefore, they quickly condense back into the liquid before reaching the surface, so no steady vapor generation takes place. Example of this boiling is heating water just below its boiling point. In simple words, when water is heated at 90 degrees Celsius on a hot plate, bubbles appear near the plate, but vanish in the liquid. Now let's understand what is saturated or bulk boiling. So, if the liquid temperature is equal to the saturation temperature, the boiling process is called as saturated or bulk boiling. In this case, the bubbles formed at the surface eventually condense in the liquid. So basically, when the temperature of a liquid is the same as its saturation temperature or boiling point at a given pressure, the boiling process is called saturated or bulk boiling. In this condition, the liquid is ready to change phase into vapor, and the heat supplied to the liquid forms vapor bubbles at the heating surface. These bubbles rise through the liquid and usually reach the top surface and then release vapor into the vapor space. Thus, the liquid and vapor exist together in equilibrium at the boiling temperature. Example of this boiling is water boiling at 100 degrees Celsius in an open vessel at atmospheric pressure. At this temperature, bubbles rise and escape as steam. Now let's see what is saturated or pool boiling. So, when heat is added to a liquid from a submerged surface and the liquid is maintained at saturation temperature, then the process is called as saturated pool boiling. So basically, when heat is supplied to a liquid using a submerged heating surface and the liquid is already at its saturation temperature or boiling point, the process is called saturated pool boiling. In this condition, the heating surface continuously generates vapor bubbles that rise through the liquid and escape into the vapor space. And hence the liquid and vapor remain in equilibrium at the boiling temperature, and the vapor formed can be collected for further use. Example of this boiling is a kettle reboiler in distillation, where liquid at boiling point is heated by steam coils submerged inside it. Now let's understand in detail what happens inside a boiling system with a submerged surface. So as we know, in boiling, bubbles form at the heating surface, rise, and disengage into vapor space. Then vapor is collected and removed continuously in equilibrium with the liquid. But let's consider a case where the liquid temperature equals its boiling point for the given pressure, and heat is supplied through a hot submerged surface. So now as heat is supplied, vapor bubbles form at the heating surface, rise through the pool, and escape into the vapor space above the liquid. Then this vapor accumulates above the liquid surface and is continuously removed through a vapor outlet. Thus, pool boiling of saturated liquid results in vapor leaving in equilibrium with the liquid. Thus, the vapor leaving is in equilibrium with the liquid at its boiling temperature, and this equilibrium behavior makes boiling highly predictable in industrial operations. Next, let's understand why is surface tension important in boiling. So, the surface tension of a liquid against the heating surface is very important because it controls how easily bubbles can detach. But why this is important? So, if bubble detach easily, fresh liquid quickly reaches the hot surface and improves boiling efficiency. But, if bubbles spread and stick to the surface, they block the fresh liquid and reduce heat transfer. So, now let's see how this works in 3 different cases. So first case is if the surface tension is high. So, when surface tension is high, bubbles don't come off quickly. Instead, they spread out along the surface and form a thin vapor blanket. This blanket covers the heating surface and blocks fresh liquid from touching it, so the heat transfer becomes poor. Then next case is if the surface tension is low. So when the surface tension is low, the liquid wets the surface well. In this case, bubbles detach easily and rise upward. And as soon as one bubble leaves, fresh liquid quickly takes its place on the hot surface, which improves heat transfer. This makes boiling more efficient. Then the last case is if the liquid has intermediate surface tension. So, when the surface tension is medium, the behavior lies between these two extremes. And therefore, the bubble partly spreads on the surface before finally detaching. So, the efficiency of heat transfer is also moderate. So, in short, high surface tension reduces heat transfer, low surface tension improves it, and intermediate surface tension gives average performance. Alright, let's summarize what we learned in this video. So the first point we learned is that boiling is the reverse of condensation, and it is widely used in distillation, evaporation, and steam generation. Then second point we learnt is that boiling is not just heating, rather, it is a convection plus phase change process, governed by excess temperature. Then third point we learned is about the types of boiling. So we learned that there are three types of boiling. Where in subcooled boiling, bubbles condense before reaching the surface. Then in saturated boiling, vapor and liquid remain in equilibrium. And in saturated pool boiling, which is the most common industrial case, vapor leaves in equilibrium with the liquid. Then the fourth point we learnt is that heat transfer in boiling occurs due to free convection and bubble convection. And finally, we learned that surface tension strongly affects bubble detachment and, therefore, the heat transfer rate. So that's all about boiling and its types in heat transfer operations. I hope this video helped you clearly understand how boiling works, its types, and the role of surface tension. In our next video, we will explore the boiling heat transfer curve, which describes how heat flux changes with excess temperature. If you found this video useful, don't forget to like, share, and subscribe to Chemical Idda for more chemical engineering tutorials.